In this video, we're going to be talking about trigonometric integrals, which are just integrals that have a whole bunch of trigonometric expressions in them, sine squared, cos cubed, whatever else. Now, the basic strategy is to take all of the different trigonometric identities that are out there in the world and use some of them in special ways to try to take these trigonometric integrals that we don't know how to do, that are hard, and transform them via identities into ones that we can do by just a simple U substitution, for example. Now, before we do this, let me just review my favorite way to understand trigonometry, the unit circle. The basic idea is this. You have a unit circle, one of radius length 1, that's what we mean by unit. I put the point on the circle that's sitting here at the point 1, 0, and then I rotate counterclockwise. And as my point goes around this circle, at any point it creates a triangle that is a right triangle with angle theta. Because this is a unit circle, the hypotenuse has length 1, and what that means is if I take something like sine of theta, which is opposite over hypotenuse, when the hypotenuse is 1, then sine of theta is just the opposite. So for this vertical strips, the opposite, I can put sine theta, and for the adjacent, the horizontal base, I can write cosine of theta. This is, in some sense, the definition of sine of theta and cos of theta. This is how I can graph sine of theta and cosine of theta, and more importantly, I can get a whole bunch of different identities from the unit circle. For instance, there is the Pythagorean identity. Now, Pythagoras applies to any right triangle, of which this is just one, and it says that the height squared plus the base squared is the hypotenuse squared. So in this context, sine squared plus cos squared is 1. And then from this identity, I can get two more of these so-called Pythagorean identities. The second one comes from dividing everything by cosine of squared. Sine squared over cos squared is tan squared. Cos squared over cos squared is 1. And 1 divided by cos squared is secant squared. And likewise, the third comes from dividing everything by sine squared. Okay, so now let's go back to integration. So the first one I'm going to do is actually one I don't need an identity for, one I can do by calculus 1 methods. I've got the integral of sine squared cos of x dx. Because it looks like something squared, I'm going to make that something to u. My u is sine of x, then my du is cos of x dx. Plugging this in, I get the integral of u squared du. I want to pause and note that that du was really important. We had a cosine, right? Like, we needed the cosine to get the du. Regardless, I can integrate that. I get u cubed over 3 plus c as it's an indefinite integral. And then when I substitute back in for x, sine cubed of x over 3 plus c. Pretty straightforward, just a u substitution. But if I make it just a tiny bit more complicated, sine squared cos cubed, notice that I cannot do that anymore. If I tried to make u equal to sine of x, then my du is cos of x, but I don't just have cos of x dx. I have cos cubed of x dx. So this doesn't work. If I try to make my u the cosine of x, then my du is the minus sine of x dx. But I don't have just a single copy of sine, I have two copies of sine. Again, this does not work. So what can I do? Well, I'm going to employ that identity. I'm going to employ the Pythagorean identity that sine squared plus cos squared is 1. And if I do this, well, I could take the sine squared and turn them into some cos squared terms, but then everything would be coses. There'd be no du if I set my u as cos. However, if I go and take that cos cubed, and I rewrite that cos cubed as a cos squared times a cos, I can take two of the cosines and manipulate them by the identity. That is, I'd have the initial sine squared, then the next cos squared would turn into 1 minus sine squared, and then I have 1 more cos of x dx. Then I can clean it up even more, sine squared minus sine to the 4th of x, all multiplied by cos of x dx. And this is why it is so useful to have that cos of x, because now I can set my u equals sine. I can set my du to be cos of x dx. And in that case, I just get u squared minus u to the 4th du. Now this is just a polynomial. It's going to be u cubed over 3 minus u to the 5th over 5 plus c. And when I substitute back in, taking that u equal to sine of x, I get sine cubed of x divided by 3 minus sine to the 5th of x divided by 5 plus c. So in other words, this is basically just do a Pythagorean identity in a clever way so that I can do my u substitution. But what if I confuse it again? What if it is now sine squared cos squared? I can't do the Pythagorean identities anymore. If I take two copies of sine squared, I can make them two copies of cosine squared, but then it would be all coses. I can take those two copies of coses and turn them into sines by Pythagorean identity, but then it would be all sines. There'd be no possibility of a du. So what can I do? Well, thankfully there are more identities. The next ones I'm going to show you are the so-called half-angle identities. They take sine squared or cos squared, and they make them 1/2 1 minus sine 2x, in the sine squared case, or 1/2 1 plus the cos 2x in the cos squared case. So in this case, where I have sine squared times cos squared, I'm going to apply the half-angle identity for both of those. I get the 1/2 1 minus cos 2x and the 1/2 1 plus cos 2x dx. Okay, now, two things being multiplied, so I have to go and expand them out. And of my expansion, well, let me look first at the red arrows. The red arrows cancel. It's 1/2 cos 2x and minus 1/2 cos 2x. They cancel. But the blue arrows remain, so what do I get? 1/4 minus 1/4 cos squared 2x dx. Now, this is pretty good. However, the cos squared of 2x term, I still cannot integrate that. I don't have a good method for cos squared, but I could take that half-angle identity and I could apply it not to cos squared of x, cos squared of 2x. So what do I get? Well, the 1/4 comes out the front, then minus the 1/4 again, and I get a 1/2 1 plus cosine, not of 2x now, of 4x, because I was applying it to cos squared of 2x, so I have to go and multiply that by 2, so 4x. Now this is an integral I know how to do, so I can get x over 4 minus x over 8 minus 1/16 sine of 4x plus that value c. So in this example, we had to use very different trigonometric identities, but it still gave us an answer that was tractable, that was doable after a little bit of work. Now, if I give you something like sine to the n, cos to the m for various n and m, can I have a strategy for the entire class of problems? Well, if either the n or the m happen to be odd, I could do what we did in the Pythagorean example. And when we had cos cubed, we took 2 powers away of the cos squared, and we left 1 cos behind to become my du. I could do the same thing if it was cos to the 5th, cos to the 7th, cos to the 9th, and likewise if it was the sine term that was the odd one, I could have done it there as well. But if they are both even, as in that last example, I have to use the half-angle identity first. Final point. Sine and cosine work well together. We have these identities that relate them. But tan and secant work well together, and cosecant and cotangent work well together. There's, for example, Pythagorean identities for each of these 3 pairs. Now, the big idea here is not that there is one strategy, one method for every type of integral that has trig terms in it. In fact, there's so many different identities out there and so many weird special cases that it would be very long and hard to try to even attempt to exhaust all the possibilities. But if we have a little bit of foresight, if we think about it, if we anticipate what is going to be our u, what is going to be our du, what trig identities can I use to get me there, then we can articulate a strategy that lets us solve a huge number of these trigonometric integrals.